Hey everyone, and welcome. So, have you ever wondered how a roller coaster actually stays glued to its tracks when you go upside down through a massive loop? Or why you get completely squished against the door when your friend takes a really sharp turn in their car? Today, we are diving deep into the counterintuitive, honestly kind of mind-bending physics of moving in circles. We're going to break down centripetal acceleration and centripetal force, and by the end of this explainer, you're going to know exactly how the universe handles a curve. Let's get right into it. Okay, let's start with a bit of a paradox. If you think back to Newton's first law of motion, it's pretty unambiguous, right? An object with zero resultant force acting on it is either going to sit perfectly still, or it's going to keep moving in a perfectly straight line at a constant speed. It basically just wants to chill in equilibrium. But we look up at the sky and see satellites orbiting the Earth in circles, or we jump on a Ferris wheel. So if objects inherently prefer straight lines, what invisible hand is out there forcing them to constantly turn? Section 1. Decoding circular motion. Let's look at how something can seemingly move at a constant speed, yet totally break all the rules of a straight line.
Now, to figure this out, we really have to look at the crucial difference between speed and velocity. Speed is just a scalar. It's just a number. It's like saying, hey, you're going 50 miles per hour. That's it. But velocity is a vector. It definitely cares about how fast you're going, but it also desperately cares about the direction you are going in. So if an object is traveling in a circle, its direction is literally constantly changing, and because the direction is changing, the velocity is changing. Mathematically speaking, any change in velocity means the object is accelerating. I know it sounds crazy, but yes, even at a constant speed, a turning object is always accelerating.
So here is the absolute crucial point. To make an object accelerate, you must apply a resultant force. No exceptions. In circular motion, we call this the centripetal force. By definition, this force is always acting directly towards the center of the circle, in the exact same direction as the acceleration. And because it points inward while the object is trying to move forward, it always acts at a right angle, or perpendicular, to the object's instantaneous velocity. Before we dive deeper, I just want to quickly say, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's keep going. Let's ground this with a classic, everyday example. Imagine you're swinging a ball attached to a string in a horizontal circle right above your head. You know the feeling, right? Well, the tension in that string is exactly what's providing that inward centripetal force. But what do you think happens if you suddenly cut the string? Without that tension, the centripetal force instantly vanishes. Poof! Gone. The ball doesn't fly outward from the center like a lot of people assume. Instead, completely obeying Newton's first law, it instantly travels in a straight line right along the tangent of the circle from the exact moment of release.
Section 2. The math of the curve. Let's see how all this builds into the fundamental mathematical rules of the game.
Let's actually apply this to a real-world calculation. Think about a standard spin dryer drum in your laundry room. Let's say it has a radius of 50 centimeters, and it's spinning at a really fast 720 revolutions per minute. First step, we convert that to angular speed, which gives us about 75 radians per second. From there, we find the linear speed at the drum's outer edge, which is roughly 38 meters per second. But look at the third step. Using the formula A equals v squared over r, the acceleration towards the center is a massive 2,800 meters per second squared. That intense, crazy acceleration is exactly what squeezes the water right out of your wet clothes.
And this brilliantly illustrates how we arrive at our master equations. If we recall Newton's second law, force equals mass times acceleration, we can literally just plug in that circular acceleration we just calculated. That gives us our ultimate formulas for centripetal force. Force equals mass times velocity squared over radius. Or if we're using angular speed, mass times radius times omega squared. These equations, right here, are the keys to understanding the universe's curves. Section 3. Real-world centripetal forces. Okay, let's step out of the abstract math for a second and look at how this plays out in our everyday lives. But really quickly, stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, back to the real world. So, centripetal force isn't some brand new physical force you haven't heard of. It's really more of a job description. Different natural forces apply for the job depending on the exact situation. For a satellite in orbit, gravity is the one providing that inward pull. For charged particles zipping through a magnetic field, magnetism provides the arc. When you drive your car around a flat corner, that's just the friction between your tires and the road. And for a banking aircraft, it's actually a horizontal component of the aerodynamic lift.
But, as you can imagine, the stakes are pretty high when these forces fail. If you try to take a sharp corner in your car on a really oily, icy, or just terribly slippery road, the frictional force might simply not be large enough to meet the demands of that mv²/r equation. The result? The centripetal force completely fails, and your car just obeys Newton's first law, carrying right on in a straight line. Basically, you skid.
Now think about your own physical experience inside that turning car. You often feel like you're being violently flung outward, right? Well, actually, what's really interesting here are the biomechanics. The car seat is pulling your lower body inward. It's providing that centripetal force below your center of mass. But your upper body? It just wants to keep going straight. Without an equal force pushing on your shoulders, your body essentially rotates around its center of mass, which gives you the very convincing illusion of an outward push. You aren't actually being pushed out. The car's just being pulled in, away from you. Mind-blowing, right? Because relying solely on tire friction is, frankly, pretty risky, engineers use physics to cheat. By banking a curve, meaning angling the road itself, the normal contact force of the road pushes up at an angle. This can then be resolved into vertical and horizontal components. That horizontal component steps right in to act as the centripetal force, drastically improving safety. Aircraft do the exact same thing when they bank, tilting their lift force horizontally to safely change direction without just skidding out of the sky. Section 4. Extreme circular motion. We've seen the everyday stuff, but now let's explore extreme circular motion, where these forces have massive engineering and biological consequences.
Consider a laboratory centrifuge. It spins mixtures at incredibly high speeds. Now remember our master formula from earlier. Force relies heavily on mass. Because more massive particles require significantly larger centripetal forces to stay in that super tight circular path, they can't maintain it as easily as lighter particles. As a result, the heavier particles just drift outward, neatly separating from the less massive ones. It's a seriously elegant application of basic physics.
And, we don't just spin test tubes, we spin humans. Take the massive NASA centrifuges, for example. Space agencies use these huge, high-speed arms to subject astronauts to intense centripetal accelerations. They use the exact same formulas we've been discussing to safely simulate the crushing g-forces of rocket launches and atmospheric re-entry, testing the absolute limits of human physiology. It's incredibly intense stuff. All right, let's move to our final challenge, vertical circles. Think of a big wheel or Ferris wheel ride at a theme park. Horizontal circles are relatively easy because gravity just acts downwards while centripetal force acts inwards. Simple. But in a vertical circle, your position relative to gravity is constantly changing, meaning the contact forces from your seat are locked in a continuous, dynamic battle with your own weight.
Let's break down that battle. At the absolute bottom of the ride, the normal contact force from your seat has to do double duty. It must support your entire downward weight, and it has to push extra hard upwards to provide the inward centripetal force. That is exactly why you feel so heavy at the bottom of a loop. But at the top, both your weight and the seat's push are pointing inwards towards the center. Gravity is actually helping provide the centripetal force, meaning the seat doesn't have to push nearly as hard. And that's exactly why you feel delightfully light at the top of the loop.
And honestly, this leads to a super fun party trick. If you swing a bucket of water in a vertical circle, won't it spill all over you when it's completely upside down at the top? Well, not if you're going fast enough. At the critical minimum speed, gravity itself provides 100% of the required centripetal force. The math tells us this happens when velocity squared equals gravity times radius. So for a 1.2 meter rope, if you swing it at exactly 3.4 meters per second, the water is effectively in free fall along the curve of the circle, and not a single drop will hit your head.
So, from laboratory centrifuges to roller coaster loops, the rules of circular motion completely govern the universe around us. It's a delicate, beautiful dance of speed, mass, and invisible inward pulse. Before we wrap up, I want to remind you that students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I'll leave you with this. The next time you turn a corner in your car,
Take a second to look past the movement. Ask yourself, what invisible force is really pulling you toward the center right now? Keep asking questions, and I'll see you in the next explainer.